Everyone, I'm Raphael. I'm from the Fraunhofer Institute for Open Communication Systems in Berlin. And today I'm going to talk about the framework we developed, and we consider this one of the first high-level programming languages for gate-based quantum computers, which are actually compilable. So let's get right into it. Here we see a little outline of my talk. I will first give an overview over high-level programming languages in general. Then I will give an overview over the structure of our framework. I will highlight the high-level coding. I will talk a bit about our gate-based infrastructure, and I will also talk about how we interface to actual backends. I will give a summary, and if there's additional time left, I hope to show you some additional code examples. All right. Okay, so how do we program quantum computers today? So many of the actual interfaces to quantum computers are very similar to assembler languages. Meaning that the focus is on concatenating gates and wires, and most quantum computing APIs use circuit objects to encode quantum programs. So how does this compare like to a high-level language? So on the left side, we have a representative of a low-level way of programming assembler, and it is characterized by having like repetitive and pedantic syntax. However, there's a high degree of optimization possible, and there's a high degree of technical knowledge required. On the other side, we have Python as a representative of a high-level language, and it allows you to have an automated and flexible syntax. It's possible to write stuff really quickly, and it's also possible to learn it really quickly. So regarding quantum computation, high-level programming could bridge quantum computation more into the direction of computer science, which could yield an increased influx of scientists which actually research in this field, which could maybe lead to more progress. And there are actually already high-level programming languages available, for instance, Silk. However, they are rather theoretical because they have no way of compiling them into circuits. However, we can learn something from Silk, and that is that there's a lot of complexity which can be hidden from the user, which is currently there in frameworks like Qirisp. Right, so let me give you an overview over our framework structure. So on top, we have the high-level language. I will give an example how you can code in this high-level language. In the middle, we have the gate-based infrastructure, which is something most of you are going to be familiar as something like Qirisp. And on top, on the bottom, we have the backend interface. I will also say a few words about that. Okay, so Qrisp is a language inside Python, and we originally built it on Qirisp, but we now have our own gate-based infrastructure. This is because of multiple reasons. One reason is that some of the features we intended were not compatible with the Qirisp architecture. Then we wanted to prevent vendor lock-in, and finally the Qrisp language is part of the compiler project, which is aiming to be to achieve technological sovereignty in Europe. And yeah, so the central building block of Qrisp is the quantum variable, and you will soon see some examples of a quantum variable. So how can we actually achieve really high-level coding? We do this by automating as much of quantum programming as possible, and this allows us to formulate our algorithms much quicker and human-readable. And some of the automation tasks that Qrisp performs is automated circuit management, automated qubit management. We de- and encode the measurement outcomes into human-readable labels. And we have a uncomputation model, however, that is not really finished as of right now. So yeah. Okay, so I will demonstrate a code example. And in this example, the goal is to employ Grover's algorithm to solve like a really simple equation. But obviously it's an example to show you the features that Qrisp can give you. All right, so I'm going to try to use this laser pointer thing. Does it? No. Yeah, all right. Okay, so the first step we're doing is we are importing some classes. And yeah, so the thing you see here is a quantum float and a quantum bool, and those are both subtypes of the quantum variable. And of course, they have their very own specific methods and so on. So yes, and here finally, this is the method for applying a Hadamard gate. Okay, first step of actual coding is creating a quantum float object, and the 4 here stands for a mantissa size of 4, and the -1 stands for an exponent of -1. And next, we will apply an H gate onto all the qubits of the quantum float, as it is usual in coding Grover's algorithm. The next step is to determine the amount of Grover iterations. I guess most of you are going to be familiar with how Grover's algorithm works, so I'm not going to go into the details of this formula. So next thing we're going to do is we will create a quantum bool, and we do this to basically perform the phase flip, which is required in the oracle. And we set this quantum bool to true using this slicing operation. This is basically the way in Qrisp how you initialize variables. So if I had a quantum float here and I would do this slicing operator here, I would then I could just put a number there, and then this number would be encoded into this quantum float. And yeah, then we just perform the Grover iterations. For this, we import the diffuser function, and then we alternate between applying the oracle and the diffuser. And finally, we will retrieve a measurement using the print function. This is obviously not the only way to retrieve a measurement. There's a specified method for this, but let's forget about this. Okay, so some of you might be wondering, okay, well, what does happen in this square root oracle function? And I will get to this in a second, but first I will show you that this is actually compiled to the circuit level. Here we see the H gates, which were initially initialized on the quantum float we created. Then here we see the X gate, which flipped the quantum bool to true. And yeah, then we just see the Grover iterations, which is alternating between the oracle and the diffuser. And because our search space is so low, it's only 2 Grover iterations. But much more wouldn't have fitted on the slide. All right, so this is the oracle. And here you can see that in contrast to many other frameworks, you don't actually have to care about where to plug your qubits and what kind of gates you use or anything. This is just a Python function of Python variables, and yeah, that's basically it. Okay, so what do we do here? Again, we first import some functions, and the first command is evaluating the square. So yeah, this employs a multiplication algorithm and returns another quantum float, which is now called ancilla, where the result of this multiplication is stored in. And then we enter something we call a quantum environment. And everything that happens inside this code block here is conditioned on ancilla taking the value 0.25. And yeah, this basically then performs the phase flip, which is required for Grover's algorithm. And finally, we want to reuse the qubits of ancilla, so we need to uncompute ancilla. And we do this by entering yet another environment, this time the invert environment, which basically implies that everything happening inside this code block here is staggered. And here we see the qmult function, which is basically the same as the infix version here, but this time we can specify a target where to calculate the result into, which allows us to conveniently uncompute the ancilla qubit. And finally, we will tell the qubit manager that the qubits of ancilla can be released and reused, and then the oracle function is basically done. And I will show you the circuit. And yeah, we can see here what we saw in the high-level code. We see the evaluation of the multiplication. Then we see the compilation of the condition, this condition here, after the condition is compiled, this qubit contains the Boolean value of the condition. And then we have here qubit 15, which is the quantum bool I talked about earlier, and the controlled Z gate will flip the face if this condition is true and doesn't otherwise. After that, we will uncompute the Boolean value and perform the and also uncompute the ancilla, which is this line of code here. So something I want to highlight here is so the qmult function requires an ancilla qubit, this one here, and because this ancilla qubit the quantum variable required for this computation is deleted afterwards, it can be reused. So in this case, it is reused as the condition truth value. And obviously, after the condition truth value is uncomputed, the qmult dagger function can again reuse the uncomputed qubit. And this is a plot of a simulation, and it's basically what we expect. The values of minus 0.5 and 0.5 are the results of our algorithm. Okay, so I'm going to say a few words about the gate-based infrastructure. Basically it's very similar to Qiskit. The naming and the architecture, everything is like rather similar. So if you're familiar with that, you're going to get used to it really quickly. And it's also the case that in many cases, if you have a program that creates a Qiskit quantum circuit, if you just replace from Qiskit import quantum circuit to from Qrisp import quantum circuit, in many cases it just works. So some features we support is controlled gate synthesis, we have parameterized circuit, we have unitary matrix calculation, and we can even do this symbolically, which is something you cannot do in Qiskit. So basically what I mean by this is if you have a parameterized circuit and you calculate the unitary, you will get back an array of SymPy expressions where you have the SymPy symbols, which are the parameters here. We have a very basic transpiler, and we can also do logic synthesis. Okay, so let me talk about the backend interface. So currently, so as I told you, Qrisp is a part of the compiler project, which is funded by the German government to achieve technological sovereignty. And we want to connect Qrisp to a German hardware producer. And we want to do this by using state-of-the-art interfacing technology. And you do this by either using OpenAPI or the Swift API. We're not entirely sure yet what is the better approach, but we'll see about that. Of course, as of right now, nobody supports our interface, so we have the possibility to run the circuits which Qrisp produces on IBM or Continuum hardware using virtual backend objects. And to ensure that when you're running a circuit, there's no like extra information transmitted to the simulator or something like this, we run every query through the interface and by contacting a locally run server. And this interface can be quite handy because imagine the situation you like have a circuit which requires a lot of power, and you don't want to run it on your laptop, but your university has a very powerful computer, then you just can very easily set up a Qrisp server and import this and connect it via the network interface, and just use Qrisp as usual, and all your simulations will be performed on your powerful machine. Okay, so here's a little comparison between OpenAPI and Thrift. OpenAPI is probably the more recent technology. It has very many convenient features like secure transport, user authentication, load management, and native API key management. On the other hand, we have Thrift, which might be a bit older, but it has the convenient feature of compiling the data to binary, which means it is fast. It's possible to have manually implemented API key management, and the Python implementation of it supports recursive data structures, which means you can also transfer synthesized gates. Okay, so let me say a few words about the virtual backend, which I already mentioned. So this is basically a way to tell Qrisp how to dispatch your circuit. Here you will see a wrapper of a virtual backend actually, which is the virtual Qiskit backend. And what this virtual Qiskit backend does is it takes an actual Qiskit backend and it transforms it into a Qrisp backend. And then you can just call the getMeasurement method with the backend keyword, with this backend keyword, and it will use the QASM simulator to evaluate your circuit. Okay, so let's get to the summary. So, in order to advance the realm of quantum computing, I believe it's key to make this discipline as accessible as possible. And we showed that it is possible to automate many repetitive programming tasks. And with Qrisp, we allow to have quick formulation of efficient programs. We can do high-level algorithm research because we don't need to care about all that bookkeeping stuff. And we have a systematic interface for exposing quantum backends to the internet. Okay, so also let me say a few words about the availability. Unfortunately, there is an issue with the licensing right now. Even though the code is fully operational, we cannot publish it. But you can subscribe to our mailing list, which is this QR code here if you're interested. And we also uploaded the documentation. The documentation is also basically done. So it's very in-depth, and there are much more features present than I was able to show you in this talk. And these two links will be available at the end too, so don't worry about them being gone. Okay, so I guess we still have time for the additional coding examples. Okay. So first code example is the quantum dictionary, which is basically something very similar to a regular dictionary. You can just put in values, and you can also retrieve the values as you are used to. But the big difference is if you give a quantum variable as a key. And we do this here by creating a quantum char. We set this quantum character into superposition by applying an H gate onto the zeros qubit, which means we are in this state here now, A plus B basically. We can verify it. We're actually in this state. Okay, and then we can query the quantum dictionary and put in the key here, and it returns the value quantum variable, and this gives us the state. This state. So A is now entangled to 42 and B is entangled to 21, which is what we put in the quantum dictionary. We can check that this is actually the case, and we're good. Second example I'm going to show you is about quantum loops. Here we have two quantum floats. one quantum float called n and another called qf. We initialize n with the value 4. We set it to superposition, which gives us that the quantum float is in a superposition of 4 and 5. And then we perform successive addition of increasing numbers, which is something you might know from the Gaussian formula. And then we evaluate the quantum float, which gives us 10 and 15. And this is exactly what we expect from the Gaussian summing formula. All right. Thank you very much for your attention. It was a pleasure. And I'm happy to have your questions.
So one of the advances is that you can compile these high-level descriptions into circuits that are conceivably runnable. Yeah. Do you have a notion of like your target runtime? Because it depends what you're targeting, at what set of gates you're allowed to bottom out on. Does that make sense?
Yeah. So basically, these are questions which I believed have to be solved like behind the interface, like putting together the right basis gates, and this is something like we're not concerned as a high-level language provider. This is rather something I believe that the backend provider has to do. So, yeah.
But like, I mean, you must do some compilation. Like you could just have that box that says multiply 2 quantum floats and be like, it's compiled. So you just need the hardware to implement this operation.
Of course, below the hood, the circuits and all, they are implemented. As of right now, they use CX gates as the basis. But obviously, you can convert it between, ion-based quantum computers. But yeah, I really believe that it is something the backend provider needs to do.
Yeah, I mean, so for reference, one thing, there's 2 different operational environments. One is like these near-term devices where you can do arbitrary rotations, single qubit rotations, and then like you're probably bounded by how many CNOTs you do, versus in an error-corrected regime where you can do as many Clifford operations as you want, but any arbitrary rotation is going to be the bottleneck. So there's sort of 2 different target environments that you might want to compile to.
We have some way of we have some intention of dealing with error correction in the plan of our project, but as of right now, we're not at this place. So probably maybe in 1 or 2 years.
Okay, thanks.
Hi, I was wondering if you could offer a comparison to Microsoft's Q#, which I believe is advertised often as a high-level language with support for compilation to circuits. I was curious what the difference is.
Yes. So the big difference between Q# and our framework is that Q# doesn't offer you possibility to transform it into circuits, and our framework is completely Python-based. Which means you have access to all the Python libraries that the whole Python ecosystem provides. While in Q#, you're restricted to what is happening inside their language.
I believe Q# does have a backend that supports, serializing a Q# program to a circuit.
Okay, so I'm not aware of that.
Okay, thank you.
Let's take one more question.
Could you show the code example from the beginning again? The one with the sort of implementations of the multiplication sign.
You want the oracle or Gro?
Good. So can you just explain what is the semantics of the line ancilla equals QF times QF?
Again?
What does that line mean?
Well, it basically invokes the multiplication algorithm, so quantum multiplication. Then it creates a quantum float and performs this multiplication into this quantum float, and then returns the quantum float, and then this is stored into the ancilla variable.
And this is different from QF ancilla written 5 lines further down.
Yes, this is in a way it's different because here you cannot specify the target variable, and here you can specify it by just giving it here. Here it will be created and returned, but here it's not returned, or it's also returned, but you can also specify the target.
And it doesn't matter that QF is a quantum variable. I can just use it twice.
Again?
So QF is a quantum float.
Yes.
And it doesn't matter that it's a quantum variable. So there's no worrying about linearity in this type theory.
Well, to be honest, I don't understand the question. The multiplication is overloaded, so
Okay, let's talk afterwards.
all right.
All right, thanks. Let's thank the speaker again.